Good day, grade 10s. This is Elton from Maths and Science series. Today I'll be doing waves, sound, and light. But before we continue with the lesson, I would like to thank those who subscribe to the channel. If you haven't subscribed yet, please just do that. We have something known as a pulse, so you must know how to define it. So a pulse is a single disturbance that is propagated. The word propagated means or moved from one point to another in a medium. So this is the definition which you must know. 2 marks. So when you talk about the medium, we're actually talking about the rope or a spring. So a single disturbance that is propagated or moved from one point to another in a medium. So this is the representation of a pulse. So a pulse is something that looks like this. And we have two terms of a pulse. So do you see that dashed line? It is known as the amplitude of the pulse. So that's the amplitude of the pulse. So it is very important for you to know that we only have two terms, and from this point to that point there, this is known as the wave length. The wave. Let me just study that first. The wave length of a pulse. So its symbol, it is the lambda. The lambda. So the amplitude, it is the maximum displacement of the particles of a medium from its equilibrium position. So that's the definition of the amplitude. And the wavelength, its definition, it is the distance between 2 points that are exactly in phase, and that symbol there is called the lambda. Yeah, so that's what we've covered. All right, let us continue. We have two types of interferences or interferences. So there are two types of them, where number one, we have the constructive interference. And the second one, we have the destructive interference. So you need to know how to differentiate them, how you can, when you're looking at them, to differentiate that this is a constructive, this is a destructive, because of 1, 2, and 3. I don't know if you understand that, but we'll start with the constructive interference. So a constructive interference, one of the two types of the interferences. So a constructive interference takes place when two pulses amplify. The word amplify means sum or add. Amplify each other. When two pulses amplify each other, resulting in a single pulse with a greater amplitude. So you know that an amplitude, we get it in a pulse, right? From that previous thing that we did. Now, it takes place when two pulses amplify each other, resulting in a single pulse with a greater amplitude. So in a constructive interference, the word amplify there means when two pulses adds or sum. So in other words, in a constructive interference, the pulses they sum each other. In other words, they add or amplify each other. So let me say we have pulse number 1 plus pulse number 2, then we have 2 amplitude, or the length of the amplitude, it is 2. The first amplitude sums or adds the second amplitude. They would amplify each other, resulting in a single pulse with a greater amplitude. So we add the lengths of the amplitude. We have 2 plus 2 equal to 4. So that 4, it is the new length of the amplitude, the greater amplitude of the pulse, which is 4a. I don't know if you get that. So as these two pulses, they're pointing upwards, in other words, you are adding them together, what? A single pulse with a greater amplitude. So this one, it is the resultant pulse. This is the resultant pulse. So constructive interference takes place when two pulses adds each other, resulting in a single pulse with a greater amplitude. Then now we have the second one, which is the destructive interference. So destructive interference, this is the opposite of the constructive. So it takes place when two pulses weaken or cancel. So that weaken, subtract or cancel each other. They will cancel only if the lengths of the amplitudes are equal each other, resulting in a single pulse with a smaller amplitude. Remember, constructive with a great amplitude, but destructive with a smaller amplitude, or no pulse. It is no pulse when the amplitudes cancels each other if they have the same length of the amplitude. Okay, so as constructive interference, there are diagrams. Its diagrams, they were pointing the same direction. So these ones, one will point up and the other one will point in a downward direction. So this is the first amplitude plus the upside down pulse. So this is how you see that this is a destructive, because the pulses are weakening each other or cancelling each other. So when they ask you, why do you say this is a constructive interference or this is a destructive interference? This is a destructive interference because the two pulses weaken or cancel each other, resulting in a single pulse. So this, when as we're calculating what the resultant pulse, we did what? We summed the length of the pulses of the constructive, but here we're going to do what? We're going to subtract. So in other words, in destructive we are subtracting, then in a constructive we are doing what? We are adding. So we just subtract. Now since that first one, it is positive 3 pointing upwards, it means it is positive. Then this one, it pointing down, it means it is negative 2a. So our answer there, it is 1a. So that 1a is the resultant what? The resultant pulse with a smaller amplitude, because that 3 is a little bit bigger than 2. Now our resultant pulse, it is a, or it is 1a. So when they ask you, why do you say this is a destructive, it is because two pulses weaken or they subtract each other or cancel each other, resulting in a single pulse with a smaller amplitude or no pulse. You see that? Okay, so when the pulses weaken or cancel each other, actually when they weaken each other, they are subtracting. When they cancel each other, it's the pulses are of the same length. I don't know if you understand that. Now, sometimes they might say calculate the resultant pulse. As the first one is positive 3, then you say plus open bracket for substitution minus that 2a. Why? Because that pulse is pointing downwards and you take down as negative, then our answer it will be a. That a or 1a, it is the resultant pulse. So there is a phenomenon or a principle called the superposition of pulses, which it is the algebraic sum of the magnitudes of the two pulses that occupy the same space at the same time. So that's the phenomenon or principle of pulses. Let's come to waves. Now, the main thing which we are going to talk about, the main thing of the lesson. So we have two types of waves: the transverse wave and the longitudinal wave, but we'll start by talking or discussing about the transverse wave. So there is a representation of a transverse wave, or you must know how to differentiate between a transverse wave and a longitudinal wave. All right, so this is the representation of a transverse wave. So the definition of transverse wave, it states that the wave in which the motion of the particles move perpendicular to the direction of the wave propagation. So let me say this is point A. Here we have point B, we have point C, we have point D. All right, so this it is time in seconds, and that it is the amplitude of the wave or the pulse. Now we're doing pulse in that previous lesson or in that previous part. So from the dotted parts here or the dashed lines, still the same thing, we're talking about the amplitude. So this is the amplitude, the maximum displacement of the particles of a medium from the equilibrium position, from its rest position. So we have the amplitude, and the amplitude. So it's still the same thing. And we have point A and point B, or that upper point there, as I'm shading it, it is called the crest or the peak. Then we have the downward points, C here. Let me just shade it a little bit. This, it is called the trough or trough. This is a crest, and this, the downward here, it is the trough. Now from this point C to point D, we say that's the wavelength. You see that it is the pulse. From C to D, it is a pulse, right? But it is the wavelength. I don't know if you can see that. C, B, D, it is the what is a pulse. Now, and C and D, it is the wavelength. And D and C, it is the wavelength. Also from A and B, it is the wavelength. And A, it is what that dotted lines, it is what it is the amplitude. If you can see from A to that point, it is a pulse, and from this point to that point is a pulse. But when we do something like this, we get one wave. I don't know if you get that. That's a one wave. So a wave, we get a wave whenever we add two pulses. Then from here to here, it's one wave. Then from here to there, we have another wave. So in this diagram, we have two waves. So that's how we
determine the number of waves in the diagram. One wave, and the second wave, we have two waves. Okay, there's the amplitude, which is the maximum displacement of the particles of a medium from its equilibrium position or rest position. You must know that definition. Then a crest, it is the upper part of the wave. Then this, it is the lower part of a wave, it is the trough. Then the wavelength, it is the distance between 2 points that are exactly in phase. We will talk about points that are exactly in phase and points that are out of phase. And the most important thing about the transverse wave, which you must know, is that the direction of the direction of the particles move perpendicular to the wave propagation. So it's very important for you to know that the direction of the particles move perpendicular to the wave propagation. So this is the representation of a transverse wave. Now, wavelength is the distance between 2 points that are exactly in phase. Now we'll talk about points that are in phase and points that are out of phase. Here is a diagram. We'll talk about points that are in phase and points that are out of phase. So points that are in phase, a trough and a trough, they are in phase. A crest and a crest, that are in phase. But a trough and a crest, they are out of phase. I don't know if you get that. Now, in phase of points, or let me just say a point or points in phase. So points in phase, it is a trough and a trough, or it's a crest and a crest, or a trough and a trough. So A and B, those are what are crest. They are in phase. They are in phase. In other words, they move in the same speed and at the same time. If they ask you maybe why do you say A and B are in phase, it's because they move at the same space, at the same time, in the same space. And C and D, they are in phase because it is a crest and a crest. But P and C, they are not in phase. Then P, as you can see, even on that other side, P and T, they are what? They are in phase. Why? Because they move in the same time, in the same space. All right, from here, and they move in the same what? They move in the same space or same time. So R and G, they are also in phase. I don't know if you get that. So points that are in phase, it is a trough and a trough, or a crest and a crest. Points that are out of phase, it is a trough and a crest. I don't know if you get that. Points out of phase. Okay. Now, a trough and a crest. Those points are out of phase. So A and C, they are out of phase. B and D, they are out of phase. A and C, they are out of phase because they are not traveling at the same speed or same time. That's the reason. So A and D, they are also out of phase because A is a crest and D is a trough. Then B and C, or B and D, they are out of phase. Then you can see now P and R, they are not traveling at the same time in the same space. So P and R, that other one is going down, then other one is going up. So they are out of phase. Don't know if you get that. Now P and G, they are out of phase too. And okay, this is P and G, they are out of phase, as well as S and G, they are out of phase. O, T, and R, they are also out of phase. So points that are in phase, we say it is a trough and a trough, they're in phase. Or a crest and a crest, they are in phase. You get that? But now, points that are out of phase, it is a trough and a crest. T's and C's, not terms and conditions, but troughs and crests, they are out of phase. Okay, now we have wave A, wave B, wave C, and wave D. So A, as you can, A and it goes something like that. Even B, still the same thing, they're traveling in the same time, the same speed. Therefore A and B, they are in phase. Why? Because they are troughs and the and crests, they are exactly aligned. So A, you can see the trough there. Even here, they're traveling the same space. All the troughs and the crests are exactly aligned. So A and B, that is why I say that they are in phase. So C and D, you can see that they are out of phase because the trough there and what, and the crest, the trough here and the crest, they are not traveling, or they are not exactly aligned, so they are out of phase. So when they ask you, why do you say in B they're out of phase, maybe they drew the transverse wave, it is because they are exactly aligned when they're in phase. If they are not in phase, they are not exactly aligned. So there's something called the frequency, the number of cycles passing a fixed point per second. So the number of cycles, in other words, the number of a complete wave. For an example, let me just draw a transverse wave diagram or representation. Okay, I want to explain the number of cycles. Now, I want to explain that part. So from here to here, we have one wave. From here there, we have one wave. In other words, that's the frequency of the wave, the number of cycles passing a fixed point per second. Now, we have something called the period again. And remember, frequency is measured in hertz or meters per second. Not meters per second, but it is measured in hertz or per second. Alright, so period, it is the length of time that it takes for a complete cycle or a complete wave to pass a fixed point. So a frequency and period, they have a relationship when it comes to calculations. That is why I'm aligning them here. Alright, we're talking about the number of waves, that's the period, and that the frequency and the period, we're talking about the length of time in seconds that it takes for one complete wave to pass a fixed point. Alright, now this is the formula for frequency, F equal to 1 over T over period, and we take period as T, which is 1 over T. And if you get that, frequency or F, it is 1 over T, then frequency, it is measured in hertz or per second, which is s to the power negative 1. Then period, it is the time measured in seconds. Okay, so T over F, that's the formula for the period. So these are minor formulas which will help us to calculate the wave speed depending on the given information for that particular statement. We have something known as a wave speed. Now, its definition, for an example, f equal to 1 over t and t equal to 1 over f. These are minor formulas to help us to calculate the wave speed. So the wave speed, in definition, it is the product of the frequency and the wavelength of a wave. The product of the frequency and the wavelength of a wave. Okay, remember, a product, we get a product by multiplying. So a product, it is to multiply. Then we have something else, a sum, it is to add, then difference to subtract, quotient is to divide. In other words, as it's saying, the product of the frequency and the wavelength of a wave. In other words, we get wave speed when we multiply the frequency with its wavelength of the wave. So the formula, it is V equal to Vf multiplied by wavelength by lambda. So lambda is wavelength with velocity. It is the wave speed measured in meters per second. So if you are given kilometers per hour, you divide by 3.6 to get meters per second. Frequency, it is measured in hertz or per second, which is s to the power negative 1. Then lambda, it is the wavelength of a wave. Wavelength measured in meters. It is always measured in meters. Always measured in meters. So the wave speed is the product of the frequency and the wavelength of a wave. You get the frequency, you get the wave speed by multiplying the frequency and the wavelength of a wave. Yeah, so it's very important for you to understand and know the conversions. So now we know that wavelength is measured in meters, right? So if you are given millimeters, you multiply by 10 to the power negative 3 to get meters. If you are given centimeters, you multiply by 10 to the power negative 2 to get meters. Frequency, it is measured in hertz, or their SI units are hertz. If you are given kilohertz, you multiply by 1000 to get hertz. Look at that example there. For an example now, you have they say calculate the speed of a wave if the wavelength is 3 meters and the frequency is 10 hertz. The first thing you must do, just write the formula. V equal to F multiplied by lambda. So they asked us to calculate what the speed, the V. You see that of a wave, if the wavelength is 3 meters. We are happy here because the wavelength, it's in its SI units as well as the frequency. They are in hertz. So you multiply what? The frequency with the wavelength, then you get 30. Now write the SI unit for speed, which is meters per second. So this is how you're doing it. You get that. So the second one, calculate the frequency of a wave with a speed of 8 meters per second and wavelength of 10 millimeters. The first thing, you write the formula, F multiplied by lambda. Now calculate the frequency of a wave. We are not calculating the speed, but we are calculating the frequency. Okay. So we're calculating the frequency of a wave with a speed of 8 meters per second. We are happy because it's in its SI units. Now, 8 meters per second, it is, and okay, wavelength of 10 millimeters. Now the V, it is 8 meters per second. Now we're calculating frequency. What is our lambda, or what is the distance of the wavelength? It is 10 millimeters. We need to convert it to meters by multiplying by 10 to the power negative 3. But if it was in centimeters, we would multiply by 10 to the power negative 2 to get meters. But now we will multiply by 10 to the power negative 3. So in other words, 10 multiplied by 10 to the power negative 3, even if you didn't put them in the brackets. I don't know what I was doing there. So just use your calculator. 10 multiplied by 10 to the power negative 3, you get your answer. Then press SD if you are given in fraction. Now to get 0.01 meters, then you substitute that answer of the original or of accurate SI unit. So 8 equal to 0.01 F. Then you divide by 0.01, and on this side again you divide by 0.01. Now you make F the subject of the formula. So this will cancel. Here you will have 800 equal to F. But you must know what the SI unit for F for frequency. It is what? It is the hertz. Even if you can get the correct answer, but if you didn't put the SI units, you are wrong. Yeah, so this is what you must know. Just make sure that before you do calculations, the conventions are accurate. Now calculate the speed of a wave if the wavelength is 0.3 and the period is 0.1. V equal to F multiplied by lambda. Calculating the speed, right? Now we have the wavelength. We are happy it's in its correct SI units, and the period is 0.1 seconds. And you know that frequency and time have relationship when it comes to calculation, so you can use this formula to calculate what the frequency given that period that you're given the statement. So F equal to 1 over that 0.1 there. Then use your calculator. You will get 10 hertz. Then take that 10 hertz and substitute it to your formula. Now V, it is 10 multiplied by 0.3. Then use your calculator. You will get V equal to 3 meters per second. So if you are not given the frequency and you're given the period, what you must know is that you use this formula to calculate the frequency with the period that you are given on the statement. So frequency and period, they work hand in hand. So F equal to 1 over T and T equal to 1 over F. So these are minor formulas which will help you to calculate the wave speed if you're not given the frequency but given the period. I don't know if you understand that. So that's very important for you to understand. Make sure that the SI units are accurate. Now do this one on your own and leave your answers on the comment platform. Then I will tell you if you are correct or not correct. Just send your answer. Now we have a longitudinal wave is defined as longitudinal wave. It is the wave in which the motion of the particles move parallel to the direction of propagation. Okay, now this is a spring. It's a longitudinal wave representation. So there are these pressed coils and the stretched apart pressed coils and the compressed, you see, and stretched. Okay, so these ones that are pressed here, press and press, it's one and the same thing. So they are called compressions. See, because they are pressed or they are what? They are closely packed. So they are called compressions. Even that's a compression, that's a compression. You see that? So these ones here that they are stretched apart or stretched out, they are called rarefaction. I can draw. Look how beautiful this representation is. So these are reflections. Now compressions, in the weight compression, you see this weight here, press. So there is a press weight there. In other ways, they are pressed. So those press coils, they are compressions, and these ones, they're stretched apart or stretched out, they are called reflections. So the compressed one or the compressions are coils in a spring pressed together. Don't forget that when your teachers ask you why are you saying this is a compression, you write that or you tell that. So coils in which, coils in a spring stretched apart or out. I don't know if you understand that and get the difference between compressions and the rarefaction. So from this distance to that distance, a compression and a compression, you get the wavelength. I don't know if you see that. Compression and compression, you get a wavelength. Now from a rarefaction to another rarefaction, you get what? The wavelength. The lambda. Okay, lambda even here. So the direction of the particles here, they move parallel. Remember the direction of the particles in the transverse, they move what? Perpendicular, but here they move parallel. So these coils, you see, it's a spring. For an example, look at this. It is a what? It is a transverse wave, right? It is a transverse wave. And you can see in that weight transverse, there's an S there. There's an S, you see. Even if you are drawing, it looks like an S that is not normal. So it's an S. So that is how you can differentiate them. This is a long thing because do you know a spring, when you stretch it out, it becomes long. Yeah. So we doing sound now. Sound, it is the sensation of hearing something, and sound waves are generated by vibrations. For an example, touch your throat when you are talking. Then you will hear what? Vibration from your throat. It means that the sound that is coming out. So sound is one of the example of longitudinal wave, and we have solid, liquid, and gas. So sound travels faster in a solid phase, and liquid in a liquid phase it travels slower. In a gas phase it travels slowest. So I won't explain much here, but just know that sound travels faster in a solid phase, in a liquid phase slower, than in a gaseous phase slowest. Sound is an example of a longitudinal wave. Okay, so it is very important for you to know that sound is an example of a longitudinal wave. So we have loudness and pitch of a sound, but we'll start explaining the pitch. So a pitch refers to how low or high a sound is. So it refers to how low or high a sound is. Namely, so pitch, for an example, pitch is dependent on the frequency. This is very important for you to understand, because they will ask you this question asking pitch is dependent on what. So namely, the higher the frequency, the higher the pitch. So if the frequency is higher, it means the pitch it is also high, and the opposite is true. Now we have, let me say, I want to explain the issue of the frequency here during the transverse wave, because I told you that frequency, we are talking about the number of waves when you talk about frequency. Let me just draw another one here to explain what I've just explained. They were just okay. Now we have the first transverse wave and the second transverse wave. What you need to understand then, it is, since here we have three waves and here we have two waves. Since here we have more number of waves, it means that we have a higher frequency. Higher frequency means what? Higher pitch. So if the frequency is lower, it means the pitch is also low. I don't know if you get that. Since here we have a small or we have less number of waves, it means that we have a low frequency. Having low frequency, it tells us to conclude that our pitch is also low. I don't know if you understand that. So pitch is dependent on the frequency of a sound. Namely, the higher the pitch, the higher the frequency, the higher the pitch. The lower the frequency, the lower the pitch. Don't know if you get that. Yeah, so you must know this. It is very important for you to know that small number of waves, low frequency and low pitch.
Loudness measured in dB or decibels. Loudness is dependent on the amplitude of the sound, namely the greater the amplitude, the louder the sound. If you can see, compare the amplitudes of these two transverse waves. The first one, it has a greater amplitude, it means it has a louder sound. That other one has a smaller amplitude, it means that there's a softer sound. I don't know if you get the difference. So loudness is dependent on the amplitude, but pitch is dependent on the frequency. So it is very important for you guys to know this and do not mix them. All right, we have something known as ultrasound. Ultrasound, sound with frequencies higher than 20 kilohertz or 20,000 hertz. So for an example, 10 kilohertz, it is 10,000 hertz. 50 kilohertz, it is 50,000 hertz. So sound frequencies higher than 20 kilohertz. Now, human ears hear sound with frequencies from 20 hertz to 20,000 hertz. So that's the range or the ranging of the sound frequencies which your ear can hear, from 20 hertz to 20 kilohertz or 20,000 hertz. Now, there are medical applications of ultrasound, which you must know: to take sonar image of an unborn baby, to break kidney stones, used by dentists to clean teeth. So it is very important for you to know these three applications. Now, let's come to light. Light, we have something known as electromagnetic radiation or EM radiation. So it is the radiation whereby energy is transmitted without requiring a medium. So we discussed about transverse wave and longitudinal wave, and those waves, they are called mechanical waves because they require what? A medium to transmit or to transfer energy. So these ones, they do not require a medium, so they are called electromagnetic radiation. So there is a question which they are likely to ask: how is electromagnetic radiation generated? So always write this: it is generated by accelerating charges. EM radiation is generated by accelerating charges. It is very important for you to know that. Bear it in mind, you will be asked that question. Now we have electromagnetic spectrum, which is the full range. You must know these radiations, from radio wave to gamma rays. Just know them as I've written them there. Now, you can see that I've wrote that they all travel at the same speed of 3 times 10 to the power positive 8. That's positive, not negative. They are sorry. So they all travel at the speed of 3 times 10 to the power positive 8 meters per second squared. If you can see the gamma rays, they have a short wavelength, and the radio waves, they have a long wavelength. So these radiations, they travel at the same speed of 3 times 10 to the power positive 8 meters per second. And there is a way of knowing this: is R, M, I, V, U, X, G, where R is the radio wave, M microwave, and I being infrared, then those ones, just look at them there. Now we have something called a photon or a 14. It's a tiny packets of light. Here actually we are calculating energy. You were taught that energy is the ability to do work. So energy, it is measured in joules. Now we have two formulas for calculating what energy. You have what? You have these formulas: E equal to hf. Now E being the energy measured in joules, H, it is a Planck's constant, which you must know, 6.63 times 10 to the power negative 34. Then we have our frequency measured in hertz. Then on the other side we have E equal to H C over lambda. E is our energy, H is Planck's constant, C is speed, 3 times 10 to the power 8 meters per second. So these formulas, we use them to calculate what? To calculate energy. But it's very important for you to differentiate or to know, maybe given a particular statement, then they ask you to calculate what? To calculate energy. You must know, you must get a clue on how to choose these formula. So use this formula if you are given frequency on your statement, then use this formula to calculate energy if you are given what? Wavelength. So use E equal to HF to calculate the energy only if you are given the frequency on the statement. Then use that other one if you are given what? The wavelength on the statement. Let's just do an example to understand what I'm saying. Now, the first example, calculate the energy of a microwave with a frequency of 4.5 times 10 to the power 10 hertz. Here you are given what? You are given frequency, so we use this one. E equal to H F, or H multiplied by F, where H, it is Planck's constant, 6.63 times 10 to the power negative 34. Then you multiply it by the frequency. We are happy it's in hertz. 4.5 times 10 to the power 10. Then use your calculator. Energy equals 2.98 times 10 to the power 2.98 times 10 to the power negative 23 joules. Now let us check that other one there. So here we are given the wavelength. They're asking us to calculate the energy. So you will use this formula. Why? Because there is a wavelength. So E equal to H, which is the Planck's constant. Planck's constant, 6.63 times 10 to the power negative 34 multiplied by the speed, which is 3 times 10 to the power positive 8. Then we divide by the wavelength which we are given. We are happy because it is measured in meters. 3 times 10 to the power 24. Then use your calculators here to get your answer. 6.63 times 10 to the power negative 50 watt joules. So even if you can get the correct answer, but if you didn't write the SI unit, you are wrong. So you must know when you're given frequency, you use this one. When you're given wavelength, you use that one. So try to do these problems to see if you understood what we were doing, and leave your answer on the comment platform. Thank you. And do not forget to subscribe to the channel, like, share, and comment. Here's another thing, guys, for you to understand more and more. Attempt questions. There are things which you're going to discover when you're doing questions. So do not just take your notes and just sleep on them. Just take them and use them when you're attempting question papers, because there are new things for you to get there, to discover. Thank you.